Greetings and welcome to Distant. In the tutorial for terminal velocity that we discussed in the previous video, um, there's one thing that I suggested towards the end, which is um, to do this calculation and evaluation for various values of dp, right? So that is something that I had talked about. And we can also do a bunch of other things such as comparing different fluids and so on. Now, one thing that I did in the previous video was we compared uh, air and water or oil and water. So when we were comparing two different fluids, what we did was we considered a different variable rho f w mu w, and we stored the velocity values in a different array vw, and we evaluated this thing again and again. Now this kind of an operation can be done for, let's say, to compare two different values or three different values and so on. But let's say if you have to compare 100 different values, you're not going to define 100 different variables and do all of these calculations again and again. So and this is where actually numpy becomes very, very useful and very important. That's why I decided to cover this as well in the tutorial. So this is the second part of the previous tutorial. Um, so over here, what we'll be doing is we'll be taking the same example, but now we'll be assessing the velocity evolution for various diameters. So let's say if we have the diameters uh, in the range 1 to, let's say, 100 right? These are the diameters that we have, and we won't be taking them continuously, but let's say 1, 10, 20, and so on, right? We'll be taking multiple such diameters, and we'll be uh, evaluating um, the velocity evolution for each of these cases. Now, here is where you can very, very easily use numpy and do calculations and all of these operations very easily. So what we can do is we can make this dp as a numpy array, right? We can make the dp as a numpy array. Now let's assess the code line by line. So we have this as a numpy array, and wherever we see dp, all the calculations associated with dp will become numpy arrays. So for example, over here, this thing has dp. So this as well will become a numpy array, right? This as well becomes a numpy array. And you don't need to change anything in your formulas, the way you've written things, because the way you write, do calculations for single variables, you can do the same calculations for a numpy array. You don't need to change anything. Uh, it would take one element at a time and do perform the same calculations for each element. So for example, if you do dp squared, it will just square individual elements and return an array of the squares. If you do this calculation over here, it will multiply all of these constants and square it and divide this thing and do all of these calculations for each element in the array and return an array of all of these calculations, right? And the results obtained from all of these calculations, right? When you do this, when you subtract this and add a constant to it, uh, you will basically get an array of this thing subtracted by a particular constant. So you can do all of these calculations using numpy, right? So yeah, so this therefore is a numpy array. This is a numpy array, And this entire thing is a numpy array. That definitely means we need velocities as well to be numpy arrays, because these are the velocity profiles or velocities at different time points for each of these diameters, right? So velocity v minus 1 in this case is going to be a numpy array. So basically, the velocity that we have would be something like this. It would be, this is, let's say, at time t equals to 0, a numpy array with certain values. This would be at time equals to dt, 2 dt, and so on till you have n dt. And after that, you enclose all of that in a master list, right? So what basically happens is that at each time point, you have a number of values of velocity, and each value of velocity at a given time point represents the velocity evaluated for the corresponding diameter, right? So that is what happens. So basically, the inside of a velocity array is going to be the inside of the velocity element, the velocity list, right? Each element of the velocity list is going to be a numpy array, right? And that's why you can perform all of these operations on the numpy array, right? You can do add, subtract, and everything, multiplication, division. And finally, the outside list that encloses all of these velocities is a list. And that's why you can use append and all the other operations to as you do in lists, right? So a combination of numpy arrays and lists can be used to solve such a problem, right? So uh, this makes the problem very, very simple, and with slight modifications to your code, you can actually do these calculations. So let's see how we would need to modify the code in order to get the velocity profiles for each of the for each of the diameters, right? So let's make a numpy array of the diameters, right? So np dot array 1, 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100, right? So this basically is a numpy array of these values, and we multiply it by 10 to the power minus 3 to convert it into meters. This is in mm, so now we convert it into SI units of meters, right? Now, naturally, you would also want the initial condition to be a numpy array, because this is just the zeroth element in the velocity array is just the initial condition, and now the zeroth element in the velocity array or the velocity list is going to be a numpy array of initial conditions. So initial velocity for the particle with diameter 1 mm, initial velocity for particle with diameter 10 mm, and so on and so forth. So if you do that, you will get say, so in order to do that calculation or to store it as an numpy array, and considering that the velocity in the initial velocity for all of them is the same, we could just maybe make a numpy array of ones. So this is how you make a numpy array of ones. So if you write np dot ones 5, so that will just make a numpy array with 5 elements, all of them being ones, right? So we need to make a numpy array of ones of the size of dp, right? So we could write it as np dot ones len dp. This creates a numpy array with ones and as many ones as the size of the dp itself, right? And this has to be stored in an in a list because this is the initial condition. So right now the velocity list has just one element, which is a numpy array of velocities, initial velocities for each of the dp's, right? And by the way, this is just a numpy array of ones. We need to multiply this numpy array by v naught. So now it becomes a numpy array of v naughts, right? So this is what we have as the initial condition, and that's it. Now this is the numpy array. This entire thing is a numpy array. So two numpy arrays can be added very easily, and this is being appended to the master list, which is velocity list v, right? That's all that we need to. And if we solve for this, we'll get the velocities for all of these values, right? Now, obviously, we've given a label as air, so we are going to get the the list. Since we've given the label as air, we won't really see anything else over here. But let's see how we can plot it in a more efficient manner, assigning proper labels to this thing. So there is one thing over here, and that is the velocity. The velocity list over here is basically an array at t equals to 0, another array at t equals to dt, and so on, right? But we don't really want to evaluate the velocities of each particle at different time, at the same time. However, we want to segregate them, the velocity profiles for each particle, right? So for example, if we have to calculate the velocity profile of the 1 mm diameter particle, we would want to evaluate, we would want to access the first element of the first numpy array, the first element of the second numpy array, and so on. So if we treat this as a matrix, we would just want to access the first column for the first element, right? Similarly, the second column for the second particle, and so on, right? So each column actually contains the velocity profile of each particle, right? But once again, if we are dealing with lists, it's not as trivial to access columns as easily. So therefore, once we are done creating the list, we could actually convert that into an array as well. So let's just convert the velocity list into a numpy array. This has been created in converted into a numpy array, and now you can easily access uh, each column by just saying v all rows, comma, let's say the first column, so 0, right? That's how you can access the different columns of the list, right? Of the matrix, right? And now let's plot it. So we'll say for I in range len v plt dot plot t comma v all rows comma the ith column, right? That gives you the okay, one second. So I'll this should be len dp because we are we are accessing each particle, right? So that's for I in range len dp plt dot plot t comma v all rows ith column. That would access each column for all the rows and plot that, right? And the label would therefore be dpi, and we'll just convert this into a string. So to do that, we just write str. So that's it. And now I'll maybe clear everything and then do this calculation. So now you see I've got the diameters of all the particles and the velocity evolution for different particles, right? Now, one thing that you clearly see is that the largest particle, 0.1, has um, reached terminal settling, but smaller particles have not. Oh, sorry, the smallest particle has reached the terminal velocity, but the larger particles have not yet reached their terminal velocities, right? And if we do this calculation for maybe longer times, let's see what happens. Uh, we'll probably be able to see some segregation. Um, this might take a while. And now we see a bit more of segregation. So we see the smallest particle is definitely here. And as the particle sizes increase, the terminal velocities are still not have still not been achieved, right? If we change the fluid, let's say if we use water instead, we would see this classification more clearly. So now you see that different particles have settled at have started achieving their terminal velocity, and they've started segregating with each other. So now this is a very important principle when it comes to separation as well. So for example, if you have to separate particles of size distribution as given here, right? So in that case, if you would use air, right? If you would use air, you would not really find much segregation. You will see the smallest particle would probably be very slow, but rest of them would most probably, not most probably, actually, we've predicted that all of the rest of them would fall with the same velocity. So if you use air to separate these particles of this particular size distribution, you won't really be able to separate these particles just using air. However, if you use water to settle these particles for this separation, water would be a very efficient solvent, because in that case, you see, the small particles would settle at very low velocities, while the large particles would settle at much higher velocities. So because of that, you will be able to easily segregate them, as the larger particles would fall the first, then the second largest, then the third largest, and so on. And as whatever is the more is the distinction between, or the separation between the velocity profiles, the more the easier it is to settle these particles and separate them. So if, let's say, you're able to find a solvent that is much faster compared to these particles, where the segregation is much better compared to these particles, you'll actually be able to get an even better separation, right? Now, let's also try something else, which is we would try to uh, start a flow in the upward direction. So if we start a flow in the upward direction, the initial velocity, remember this velocity that we've taken, the initial velocity is the velocity of the initial velocity of the particle falling, right? But if we start flow initially, what would happen is that the particles would start flowing upwards and then start falling due to the influence of gravity, right? So if we start flow, the initial condition would actually be a negative initial condition. So let's start with a very small initial velocity, let's say -1, and see what happens. So now we see we don't see much difference over here. Let's go with 10. There is a slight change in the velocity profile probably, but we don't see any of that over here because of the large time scales involved. And even right now, I don't see any difference, but let's make it -1000. And now you see a considerable difference over here. So now, initially, the particles have some of the particles have uh, initially all the particles have a negative velocity, but after that they reached a zero, which means they just stopped. And now, because of the influence of gravity, they started falling downwards. So because of that, there are certain particles which are still having a negative velocity even at higher times, which implies that these particles are actually going upwards rather than going down, while there are other particles that are falling down. So this is actually the principle that is often used when you induce flow in order to uh, separate particles of different sizes. If we maybe change the initial velocity a lot more, we could see a lot more of this distinction. So now you see um, there are these particles which are falling at almost a zero velocity, while there are these particles which are falling much faster. So now the separation can be even better because these particles would fall much faster compared to these particles. If you compare it to the scenario, okay, if you compare it to the scenario where you had zero initial velocity, so there was still water in which there was a flow, in that scenario, the velocity over here, the velocity difference was maybe not as much, but over here, that is definitely the case. And especially in the smaller times. Of course, at larger times, all of them would reach their terminal velocities, but at smaller times, you can definitely uh, force some of the particles to flow at velocities to go above, while you can force some of the particles to go below. And because of that, separation could be easier. So I could actually show you these things from the plot itself. So, for example, if you consider this line over here, right? This line over here. So, or maybe let's not consider that line. Maybe let's consider the zero line over here. So this is the zero line over here. Now you see, till this time, right? Till this time, if you go past this time, these particles have started. I think I cannot see the graph as clearly. Maybe I'll remove the legend and then try to see. So I'll just remove the legend and induce, let's say, minus 3000 as the initial velocity, right? So now if I would try to see the zero line, this is my zero line, right? And let's say I consider this particular time over here. This is the time that I'm considering, right? Now, after this time, you see these particles over here, these are flowing at a negative velocity. That means these particles are actually going upwards, right? However, there are these particles, I'll use a different color. So there are these particles at these times which are flowing with a positive velocity, which means they are going downwards, right? So now, because of this, the separation could be enhanced even further because there are particles that are going up and then there are particles that are going down. The small particles over here, they have not really been able to cross zero. They've not really been able to cross zero as well. So most of these particles are actually just floating around in this water stream that is being forced in the upward direction. So these particles are not really falling, they are still over there. So because of that, the separation can be enhanced even further. So there are these So this very simple principle of how velocity evolves over time and the concept of terminal settling, these alone are sufficient to design settling units, sedimentation tanks, and because of that, this concept is very important. So now you people can uh, simulate this kind of a system on Python, and you can do multiple such exercises with Python. So for example, you could change the density of the fluid that you are using. You could maybe use you could maybe see what happens for multiple other diameters, multiple other densities. So you could see densities of the particles. So you could see how what kind of system would efficiently separate, in what kind of a system you would need to induce flow, and so on and so forth. So this is a very powerful concept, and hopefully now you are very comfortable with this particular thing. So we'll do many more such interesting chemical engineering based problems. So hopefully you keep enjoying and keep learning Python over time. Thank you.